Good afternoon, friends. Today we shall be discussing about synthesis of RLC network. When we say synthesis, we are still restricting ourselves to two terminal network, that is one port network. Now, before we go to the synthesis, we will define some functions, special type of functions. Minimum function. What is a minimum reactance function? First we define a minimum reactance function. A minimum reactance function we get when an impedance function has got no poles on the imaginary axis, that is an impedance function having no poles on the imaginary axis. That means in ZS factors of this type will be ruled out. This type of factor, there are other factors here, this type of factor is not present, then it is a minimum reactance function. Similarly, if you have in the admittance function factors of this type absent, that is there are no poles on the imaginary axis for the admittance function, then we call it minimum susceptance function. Okay. If we have the real part of Z j omega equal to 0 at some frequency, at some omega equal to omega 1, then we call it minimum resistance function. Okay. Minimum resistance function. Similarly, if you have a real part of yj omega equal to 0 at some omega equal to omega 1, we call it minimum conductance function. Minimum conductance function. If a function is simultaneously minimum reactance, minimum susceptance, minimum resistance, minimum conductance, then we call it a minimum function. Now, there are certain specific properties of the minimum functions. We will just mention about the essential features of minimum function. The first one is, say ZS is finite at s equal to 0 and infinity, at s equal to 0 and infinity. It has no poles or zeros on the imaginary axis. No poles or zeros on the imaginary axis. Because it is finite at 0 and infinity, obviously if I write Zs equal to Ps by Qs, both of them will be of the same order, same degree. So, if this is s cubed plus twice s squared plus something, this also has to be s cubed. If it is s to the power 4, if it is of higher degree, then s tending to infinity, at s equal to infinity, this will be 0 and ys will tend to infinity. So, similarly, if this is of higher order, at s equal to 0 this will tend to 0, but at s equal to ys at s equal to 0 will tend to infinity. So, it will be of the same degree, these two polynomials. Then thirdly, a real part of Zs is equal to 0 at some omega, say omega 1. That means, if I sketch the real part, maybe like this. So, at some omega 1 this will touch 0 value. What does it physically mean? That means the real part shows the active power consumed. I square into the real part is the active power consumed. At some frequency that active power will be 0 for a minimum function. Let us take an example. Let Zs be given by say twice s squared plus s plus 1 by twice s square plus 2s plus 4. Then what would be a real part of z j omega? We take m1 m2 minus n1 n2. If you remember, twice s squared plus 1 is the even part, multiplied by the even part twice s squared plus 4 minus the odd parts product divided by even part squared for the denominator minus odd part square. Okay. So, that gives me twice s squared plus twice into twice s squared 4 s to the power 4. So, 4 omega to the power 4. Okay. 4 2s are 8 plus 2 10 minus 2. So, plus 8 s squared means minus 8 omega squared plus 4 divided by 4 omega 4 twice s squared. So, 4 s to the power 4, 4 omega 4, 4 2s are 8 minus 4. So, 4 2s are 8, 2s are 16 minus 4. So, plus 12 s squared, that gives me minus 12 omega squared plus 4 4s are 16. So, this can be written as 4 can be taken out. So, omega to the power 4 minus twice omega squared plus 1 by omega to the power 4 minus thrice omega squared plus 4. So, clearly you see this is equal to omega square minus 1 whole squared. So, this will vanish at omega square equal to 1. Okay. So, when omega square is equal to 1, real part will be 0. Real z j omega equal to 0 at omega square is equal to 1, that is omega equal to 1. What would be Zs like then? Then z at omega equal to 1, how much is this? Let us see. 2 into s squared means 2 into minus 1 plus j1 plus 1 divided by minus 2 twice s squared is minus 1. So, minus 2 plus 2 into j1 plus 4, correct me if I am wrong. So, minus 2 plus 1 minus 1 plus j divided by 2 plus 2j, is that okay? So, that gives me minus 1, you see minus 1 plus j, that is magnitude of root 2 and angle of 135 degree, is it not? And 2 plus 2j is 2 root 2 and an angle of 45 degrees. So 135 minus 45, so that gives me 90 degrees. So J, so that gives me 1 by 2 J. So it is purely reactive. The impedance function is purely reactive. That was what we expected also. The real part will vanish. There is no real part at this frequency. Now this will be the starting point of our realization. Now we shall follow first the method suggested by Bruni. Bruni's synthesis starts from this point. That means Zs I can conceive as, at that particular frequency it is half J. Is that okay? So this is plus half J at omega equal to 1. So if this is the reactance, can we suggest an inductor value which will give me half J as a reactance value at omega equal to 1? So let us call that as L1. L1 into J1 is equal to half J omega. So L1 is half Henry. So let us take a half Henry inductor out of Zs. Zs I am trying to realize as a reactance which is inductance of half Henry plus another reactance, say Z1s. How much is Z1s? Therefore Z1s will be Zs minus this L1s, which is Zs is twice S squared plus S plus 1 divided by twice S square plus 2S plus 4 minus half S. Is that okay? Now at this point you just see what would be the property of Z1s, what will be the value of Z1s at S equal to J1, that is at omega equal to 1, what would be the value of Z1s? Zs is purely reactive, half J, and this is also half J. So this will be 0 at that frequency. So Z1s, let us work it out. Let us see what it gives me. If you write it, this is S squared plus S plus 2, okay. Simplify this, twice S squared plus S plus 1 minus twice S cubed minus S cubed, S into S cubed minus S squared minus twice S, okay. So that gives me twice S and S, that will give me minus S cubed plus S squared minus S plus 1. Which gives me finally, you can factorize this S cubed and S, if you take together, that will give me S square plus 1 as a factor. So minus S plus 1. Okay. So obviously S square plus 1, this factor at S equal to J omega, at S equal to J omega, S square plus 1 will be equal to 0. Okay. So that was what we expected. Z1s will vanish at that particular frequency. How do you remove this particular 0 then? You create a pole. If you remember in our earlier synthesis, you create a pole and then remove it. This becomes a 0 at that particular frequency, S equal to J. So we take the corresponding admittance y1s as 2 into s squared plus s plus 2 divided by s squared plus 1 into 1 minus s. At this moment, let us not bother about the sign, it does not represent a positive real function at this moment, but we will take care of that in course of time, we will see what it means. So, y1s can be, I can make partial fractions written as k1s by s square plus 1 plus some k2 by 1 minus s. Let us see what k2 will represent. How much is k1? K1 comes out as let us calculate the value of k1, multiply by s square plus 1, make s square plus 1 equal to 0. So, that gives me 1 plus s and divided by s, so s minus s square, so s minus s square and s square is equal to minus 1. So, that gives me 1 plus s divided by s plus 1, so that is equal to 1. Oh, there is a 2 here, no? So, there will be a 2 here. So, it is half. So, k2 similarly, if you multiply by 1 minus s and then make 1 minus s equal to 0, that is s equal to 1. So, this will be 1 plus 1 2 plus 2 4 into 2 8 divided by 2, that is equal to 4. So, you can write y1s as s by 2 into s squared plus 1 plus 4 by 1 minus s. So, what does it mean? I have got first L1 removed, then I have got a y1 and a y2. Sorry, this I will call it y2 plus y3. This whole thing is y1. So, this is y2, this is y3. Okay. So, what is corresponding z2? This shunt term, if you just inverse of this, 2 into s squared plus 1 by s, that gives me twice s. Check the value of k1. K1 I worked out 2 into s squared plus s plus 1. How much is this is z1? How much is y1? 2 into s square plus s plus 2 by s square plus 1. Is that so? I forgot to put the values correctly. K1 is equal to, if you remember K1, I multiply by s square plus 1, make s square plus 1 equal to 0. So, 2 should be in the numerator.
Yes, it will be 2.
So, it will be, sorry, 2. I was by mistake I was looking at Z1s. So, this will be 2. So, this will be 2s. So, s by 2 plus 1 by 2s. That means, this branch will be nothing but an inductor and a capacitor. Okay. So, this is half Henry, this is 2 farads, and this was also half Henry. Okay. This is what we got. Now, obviously, whatever be the part here. You see this will start resonating at that particular frequency, S equal to J1, that is at omega equal to 1 this will resonate, so that will be a short. So the entire impedance Z1s, that is what we are saying, Z1s will be 0. So Zs, the impedance value of Zs, which was half j, is the impedance of this itself. This impedance is 0 that time, because it is resonating at that frequency. So Z1s is having a 0 at that point, and that has been realized like this. What is this Y3? So from there let us see Z3. What will be Z3? 1 minus S by 4. So that is 1 by 4 ohm resistance minus S by 4. That is, I am having an inductance of minus 1 by 4 Henry and a resistance of one by 4 ohms resistance. Okay. Is that all right? What is this minus 1 by 4 Henry? How do you realize minus 1 by 4 Henry? Now Bruni suggested you have an inductor of half Henry, another inductor in the form of a T, half Henry, and this one is minus 1 by 4 Henry. Okay. These three can be replaced by a transformer, an ideal transformer, where the primary inductance is this, keep it open, so that will give me the primary inductance, half plus half, 1 Henry. Okay. Then this side half and minus 1 by 4, half minus 1 by 4 is 1 by 4 Henry, and a mutual inductance of half Henry. And then have the capacitor, resistor, how do you realize this? What is the coefficient of coupling? That is equal to m by root over of LP LS or L1 L2, and that is here half Henry divided by 1 into 1 by 4, that is equal to 1. So if you are having an ideal coupling, two transformer coils are ideally coupled and they are having the values 1 Henry and 1/4 Henry, then you can realize this network. So connect the two transformer terminals here and then connect the capacitor to this end, and the other ends are taken out like this. So this is the configuration of a Bruni's network, where a negative inductance has been incorporated in the coupled coils. So if one of the terms is negative, do not get frightened, it can be realized. I could have got right in the beginning, instead of plus Jx at that frequency where the resistance part, the resistive part was vanishing, the real part was vanishing, at that time the impedance of Zs, where we got half j, could have been negative. Then we will start off with a negative inductor, minus half j. You do not try to realize it by a capacitor. You can try it at home. If you try to realize it with a capacitor, what kind of difficulties you face later on. You can try with another example. There are many examples, many problems given in the book, or we will take up in the tutorial class. While realizing some of them, we may find a negative sign here. So there also the same logic will work. Now there is another method of realizing this, that is Bott-Duffin synthesis. We shall be discussing about the synthesis techniques, and then we will take up a large number of problems in the tutorial class. So, Bott-Duffin synthesis is a very interesting synthesis technique. Before we go to that, we define another interesting positive real function, Richard function, which says that if Zs is a positive real function, then for positive real values of k, you take any value of k, positive and real values of k into Zs minus S into Zk divided by kZk minus SZs is also a PRF. RS is also a positive real function. This is called Richard function. So, if RS is positive real, then let us extract Zs from here. Write Zs in terms of RS. You multiply the denominator by RS and then take Zs terms on one side. So, Zs comes out as kZk into RS plus SZk divided by SZs RS and KZs. So, it will be K plus S RS. Okay. Now, we can break it up into two parts, KZK RS divided by K plus S RS plus SZK by K plus S RS. Okay. If you divide the denominator by the numerator, then K by KZK, so I can write this as 1 by ZK into RS plus S by KZK, RS will get cancelled, plus similarly here K by SZK plus S will get cancelled, RS by ZK. Correct me if I am wrong. Now, let us see what will be the structure of this impedance function. This is 1 by 2 admittances. So, this is an admittance, this is an admittance. So, I can write like this. What is 1 by KZK RS? So, the first one can be written as 1 by Z1 S, so Z1 S plus what is this admittance? See, Zs is 1 by this admittance, this is 1 Z1, this is Z2, and Z1 I am writing as sum of two admittances inverse of that. So, this is an admittance of what? A capacitive element. So, a capacitor of value 1 by KZK farads. Is that all right? Similarly, this one K by SZK, so this can be written as one by ZL plus 1 by Z2S where ZL will be this inductance. So, Zk by K Henry, that will give me K by Szk as the admittance, is it not, and 1 by Z2 means this will be Z2, okay, where Z2 means I will write Z1S means Zk into Rs, इतना खांसी में रिकॉर्डिंग खराब होगा, Z2S equal to Z2S is Rs by Zk, okay. Zc we have already seen, Zc is Kzk by S, and ZL is S into Zk by K, okay, S into Zk by K. So, let us start from this point where we stopped at, we initiated for Bruni's synthesis. We will start from there for Bott-Duffin synthesis also. That is, Zk by K is that inductance value for ZL2. So, if it is positive, then Zk by K we take as that value of L. What was that value? J x at omega 1 by omega 1, okay. If you remember, we will not put J because that will be divided by J omega 1. This was taken as L1, is it not? So, we choose that value of L1 as Zk by K, because Zk by K will give me that inductance value, okay, if it is positive. If it is positive, then we will start realization from here, otherwise we will start from here. So, x omega 1 by omega 1 is L1, so that gives me K. If we get say half, L1 is equal to, in the last example we got half, then solve for K. So, let us take up that same example, we will try from there. How much was L? Half, that was equal to half. So, how much is Zk by K? Zk will be twice K squared, the polynomial was twice S squared plus S plus 1 divided by twice S squared. See, I am putting in place of S, I am putting K. So, twice K squared plus twice K plus 4, alright, this is Zk. So, Zk by K, so this divided by K is equal to half, okay. So, Zk by K equal to this divided by K, and that has to be equated to half, alright. So, let us solve. Twice K cubed plus twice K squared plus 4K equal to 2 into 2K square, 4K squared plus 2K plus 2, okay. So, let us bring all of them to this side, twice K cubed, twice K squared minus 4k square, so minus twice k squared plus 2k minus 2 equal to 0. So, k minus 1 gets common to 2k squared plus 2, okay, equal to 0. One root will be imaginary, the other one will be k equal to 1. So, we will take the real value of k, that is k equal to 1. So, once you know k equal to 1, how much is zk? Zk by k is equal to half. So, zk k equal to 1. So, zk equal to half. Okay. So, if you know zk is equal to half, k is equal to 1, calculate the Richard function, because we need for calculation of z1 and z2 this RS function, all right. So, let us calculate RS. What was Richard function? RS was given as k into Zs minus S into Zk divided by kZk minus SZs, okay, k equal to 1. So, 1 into Zs, we will substitute Zs afterwards, minus S into Zk is half divided by k into Zk, 1 into half minus S into Zs, okay. You have to expand, put Zs and expand, you will get Rs. So, let us put those values, Zs twice S squared plus S plus 1 by twice S squared plus 2S plus 4 minus S by 2 divided by half minus S into twice S squared plus S plus 1 by twice S squared plus twice S plus 4. So, this is RS. Once you have got RS, Zk into RS is Z1s, Zk into RS is Z1s, and Z2s is RS by Zk. So, how much is Z1s? Z1s is RS into Zk, and Zk we have got already the value of Zk as half. So, into half. Z2s RS by Zk. Am I correct? Z2s Z2s, let us see Z2s. I hope I have not made any slip. 1 upon RS by Zk, there was a small slip. Z1s, Z1 is Zk into RS, and Z2s should be, actually this is 1 by Z2s, so Zk by RS, is it not? Zk by RS. Now this is all right. So Z2s is Zk by RS, and that is equal to half divided by RS. So, RS, let us complete this. 2 into S squared, so 4S squared plus 2S plus 2 minus twice S cubed minus 2S, sorry, it should be 2 goes, so s cubed minus s squared minus 2s divided by 2 into this, and divided by this, and this will also get cancelled. So, let me work out here. Here it will be s squared plus s plus 2 minus twice s cubed minus s squared minus s. If you simplify this, R s will come out as minus s cubed minus s squared plus 4s squared. So, minus 3s squared plus 3s squared, 2s and minus 2s will go, is that so, plus 2. I am getting some complicated figures. Please check, there should be 2s square plus I have made a slip here while computing this. It should be 2s squared, because 2 is a common factor, 2s squared plus s plus 1. Anyway, you complete this. You can complete this anyway. R s will be whatever is the simplified form. I will just work out separately, there is a lot of mix up. What I wanted to stress is, once you have found out R s, you have already got Z1s. Z1s will be R s by 2 and Z2s will be half R s. So, the impedance function here and the admittance function here will look alike. Okay. We will complete this problem in the next class, time is running out. The other two parts are, there is a inductor here and there is a capacitor here. So, this is the kind of network you are getting. These two are to be realized. Let me work out the value of R s here. R s twice s squared plus s plus 1 minus s into s square plus s plus 2, s into s square plus s plus 2 divided by, so s squared plus s plus 2 minus s into twice s squared plus s plus 1. Is that all right? Check. Twice minus s cubed minus s squared plus twice s squared plus s squared minus 2s plus s minus s plus 1 divided by minus twice s cubed s squared and minus s squared gets cancelled plus s and minus s, that will also get cancelled, so plus 2. So, that gives me in the numerator 1 minus s into s square plus 1. Check the numerator, and this is 2 into 1 minus s cubed, which is nothing but 1 minus s will get cancelled. So, it will be 1 plus s squared divided by 2 into s squared plus s plus 1. Okay. So, this is R s, all right. What is therefore, what is our Z1 R s by 2? If you see, Z1 is R s by 2. So, Z1 s is 1 by 4 s square plus 1 divided by s square plus s plus 1. If I invert it, corresponding y1 s, it will be s square plus s plus 1 by s square plus 1 into 4. This is nothing but s square plus 1 by s square plus 1 will give me 1. So, 4 into 1 plus s by s square plus 1. So, that is 4 more plus 4s by s square plus 1. So, this is our familiar elements y1 plus y2. y1 is 4, means 1 by 4 ohm resistance, and this is y2. So, if I invert it, how much is this? If I invert it, 1 by 4 Henry and 4 farads, 1 by 4s, so 4 farads. What about Z2s? Z2s was Rs half Zk by Rs, that is half divided by Rs. So, half divided by Rs. So, we can write Rs was 1 plus s squared. So, it will be inverted 2 into s square plus s plus 1 divided by 2 into s square plus 1. So, 2 will get cancelled, it will be 1 plus s by s square plus 1. Z2s is this. So, Z1 plus Z2, I mean Z2 can be written as 2 sum of 2 components. One is 1 ohm resistance, other one is 1 Henry and 1 farad capacitor. So, this is Z2. Okay. So, now you come to the final realization. Z1s was in parallel with the capacitor. Okay. So, you have final Zs as a capacitor in parallel with that Z1s, that is 1/4 ohm resistance and network like this, and then an inductor, and this one is resistance So, this is the structure of Zs. The number of elements required here will be more. You see, it is no more canonic in that sense, because we are getting a negative inductor in case of Bruni synthesis. We coupled it with a transformer. The number of elements there we got much less. Here it will be 1, 2, 3, 4, 5, 6, 7, 8. Nevertheless, this is easier to implement. There is no coupling involved. Okay. So, thank you very much. We shall continue with this with a few more examples in the next class. Good afternoon, friends. Today we shall be discussing about parts of network functions. Now, before we go to that, I will just briefly summarize what we did yesterday in the Bott-Duffin synthesis, then we will go to parts of network functions. So, in the Bott-Duffin synthesis, we defined the Richard function, which is a positive real function in terms of ZS as KZK minus SZS. If ZS is a positive real function, then for all positive values of K, RS will also be a positive real function. From there, we wrote ZS in terms of RS as KZK RS plus SZK divided by K plus SRS, and this we broke up in this form. If you remember, in the form of two parallel elements put in series with another set of this type K by S ZK plus RS by ZK. Okay. So, this was shown to be like this. This is the admittance of a capacitor, is that all right? So, this is admittance of a capacitor. So, 1 by KZK farads will be the value of this capacitance. This is, say, this is some Z1, then in parallel with this capacitor, this impedance Z1 will come. Similarly, this one is the admittance of a reactor whose value is Zk by K, so many inductance. In parallel with that, you have Z2, which means Zk by Rs. Is that all right? So, this is what we wrote yesterday. Now, Z1 to be calculated, Z1 is Zk into Rs. Rs being a positive real function, Zk is having a constant value for a particular value of K, real value. So, this is an impedance function, realizable impedance function. Similarly, Zk by Rs is the other impedance function. You can see one is Zk into Rs, the other one is Zk by Rs. For example, if you have a complex pair like this for M1 plus M2 plus N2, one pair of roots is like this, then for M2 minus N2 correspondingly you have roots here, mirror images. So, you get quad of points. For each complex root set, you get actually quad of points for the function M2 squared minus N2 squared. Okay. So, problem is simplified. You are given M2 squared minus N2 squared in terms of omega. So, make a substitution, omega squared is equal to minus S squared, then factorize it, then choose the factors corresponding to the left plane roots, that will give you M2s plus N2s. Why left plane roots? Because original function Zs is a positive real function which should satisfy Raut-Hurwitz criteria. That means all the roots of the numerator and the denominator must lie in the left plane. So, M2s plus N2s corresponds to the function Zs, it is the denominator of Zs, is it not, which is a realizable function. So, the roots here are lying in the left plane. So, you select out the roots corresponding to the left plane. Once you have done that, then M2S plus N2S is defined. M2S plus N2S is selected. Now you choose ZS equal to, suppose this is equal to some B0 plus B1S plus B2S square. Suppose it is like this. Maybe B0 s to the power 3, B0 plus B1S plus B2S square plus B3 s to the power 3. Then what will be the numerator like? It can have A0 plus A1S plus A2S squared plus A3S cubed. Okay. Any question? The condition for a positive real function is the power of s should differ at the most by 1. Can I take A4 s to the power 4? See, by division there will be a free s term, that means some reactance element, additive reactance element will come. It can be anything, that becomes indeterminate, is it not? As I was telling you right in the beginning, I can identify from that only x corresponding to the minimum value. Any additional x will also give me the same real part. Real part remains unchanged if you keep on adding reactances. So, we will consider only that reactance function which is just required to realize Zs. N1 M2, okay. This part divided by M2 square minus N2 square. M2 square minus N2 square is already known, that is 1 plus omega to the power 6 and so on, like that. So, it is this part which has to be computed, okay, from that A0 A1, alright. In terms of A0 A1 A2 you can calculate this and substitute. Once you have calculated these coefficients, just substitute there, you will get the odd part. Otherwise, in Zs put s equal to j omega, take out the real part and the imaginary part, that will be giving you x. Okay. So, we will stop here for today. We will take up a few more problems in the next class along with problems of RLC synthesis. Thank you very much.